All right, in this video, it's time to do equilibrium calculations. Here we go. So, we're going to do math on this because there's a lot of things in science that you need to figure out that are related to equilibria that involve this type of calculation. So let's teach you how to do it. So here's the setup. You've got some reaction, you have an equilibrium constant that you're given, and then you have some amounts of starting material. You put half a molar of hydrogen gas, half a molar of chlorine gas into some flask. There's no hydrochloric acid. There's no hydrogen chloride gas. What are the concentrations of all the species at equilibrium? So we did this before, but you were told, here's the concentration of one of the things at equilibrium, and then asked to solve for the equilibrium constant. But now it's the other way around. You have the equilibrium constant, and you need to figure out what the concentrations are at equilibrium. And this is relatively realistic because you can look up equilibrium constants for reactions relatively readily. All right, and then there's a blue stripe down the side of the screen because in the next video, this video and the next videos, there's a number of different calculations, and I tried to label them as this calculation's blue, the next calculation's red, so on and so forth, so you could keep straight which problem I'm doing because they spread over a number of slides. All right, so we need to figure out which way this reaction's going, and then also whether it's X, 2X, 3X, whatever. So for every mole of hydrogen and chlorine that come together, you're going to make 2 moles of hydrogen chloride. So we'll use an X to represent the hydrogen and the chlorine change in concentration, and we'll use 2X to represent the change in hydrogen chloride concentration, because that makes sense stoichiometrically. Also, the reaction's going to the right, because there's no hydrogen chloride initially, and so Q is 0, K is 193, Q is less than K, Q is going to increase to get towards K, which involves shifting the reaction to the right to make more products. Okay, so we typically put this in this ice box, and this one I labeled find change. Our previous ones were labeled find concentration because we had a different goal in mind. Here we're trying to find the change, and so I'll put this in the box thusly and label it as such. Our initial concentrations are given in the problem, and I talked about that already. Now here's how you write the change. The reaction's going to the right, so that means it's negative X for the reactants and positive X for the products. And then for every hydrogen molecule you react, you make 2 molecules of hydrogen chloride. Okay? And then you evaluate this. The first line plus the second line equals the third line. And so the equilibrium concentration of hydrogen gas is 0.5 molar minus however much goes away. And then the equilibrium concentration of HCl is double the amount of hydrogen gas that went away, is what that says. And this makes sense with what we were just saying. So again, the whole point of these boxes is to try to just represent some logic of the problem, and it's not like it's a special thing. It just looks pretty and makes it easier to deal with. Now, from here, we have an expression for what the equilibrium constant is. You can get this from just looking at the reaction, right? Oh, HCl is the product, so it goes on top. There's a stoichiometric coefficient of 2 for HCl, so I square it. That makes sense. And then now what we do is we plug stuff in. We take the bottom line of the equilibrium concentration, and then we plug that in down into this equation for the equilibrium constant. So for example, this goes here, this goes down here, this we're just going to put into here, and then now we have this equation over here on the right. And now the equation on the right, well, 2x squared, yada yada yada, is equal to the equilibrium constant, which we know, so it's just a game of solve for x. So I just highlighted it here, and I took the denominator and made it 0.5 minus x squared, and then it's really just a math game from here on out. So let's solve for x, and then figure out what to do with it. I'll show you this the first time because, hey, a little more algebra practice, never a bad thing. We want to solve for x. Hey, look, the things on the left side, both the numerator and the denominator are squared. So look, we can take the square root of this, and then we'll get 2x divided by 0.5 minus x, like that, without the squares, and then that's equal to 13.89. 3 sig figs on this because when you do squares or exponents or square roots, it's like multiplication. So you have the same total number of sig figs afterwards. All right, let me scoot this up. Then we want to get rid of the denominator here, so we're going to multiply both sides by it. My little thing in red has the wrong sig fig, my bad. All right. Now you have to move the denominator as a unit. You can't split it up and move them individually. It gets kind of, it's wrong if you do that. Now we're here. Then we need to somehow get x all together. So what we're going to do is distribute this 13.89 into 0.5 minus x. And you get this kind of thing. Now, 2x plus 13.89x equals 15.89x. So that's on the left side. We're going to just basically add the term with x on it to both sides. That's equal to 6.945. Now finally you do the division and you can solve just for x. Awesome. Don't stop here. This is just x. It's not actually your answer. You got to then use x for something. What are we doing with x again anyways? Oh yeah, we're putting it in here. So now we need to evaluate this bottom line to then find what our equilibrium concentrations are. And there's two ways to do that. One, you make another little box. Now that you know what x is, you rewrite the whole box with the goal of finding concentrations. Your goal is not to find x. And so then top line plus the middle line equals the bottom line. And so you can just do this, and then, hey, your bottom line there are the concentrations of all the reactants. So that's one way to do it. You can write a second icebox to fill it in for what x is. Another way to do it is just evaluate the bottom line of the first box you had. So, hey, look, hydrogen gas is 0.5 minus x, so just write that down and figure out what that is. Right? Chlorine gas is the same thing, 0.5 minus x. All right. So you can just do it this way as well. Ultimately, what matters is just that you have the right answer here. So, a lot of people mess this up for various reasons. One is maybe they don't get quite how to set up the icebox or what to do with it. Another one is just algebra. I see a lot of bad algebra. And then especially later in using equilibria, when we have to do things like use the quadratic equation to find what x is, people mess that up too. So please, please, please get in the habit of double checking your answer. It's not that hard and it's worth your time. So here's our setup again, right? Hey, look, we have an equation for Kc. We can plug these numbers in that we just found, right? We found concentration of all these things at equilibrium, so it's equal to K and not Q. And hey, does this equal 193? And as long as it's pretty close, then that means you did it right. There's going to be some rounding errors here because we only know 0.063 to 2 sig figs. So, that's going to do that for us. But overall, this is pretty much the same thing. Please do this. If you don't do this and you get it wrong, it makes me think you didn't give a crap. Not the impression you want to send, right? So do this, make sure you did the math right, and you'll be okay. All right, so now we switch to the problem with a red bar down the side, which is the same reaction and the same form of the equilibrium constant, but now I'm going to show you how to do it if you start with just products. So here we have 1 molar HCl with no hydrogen gas and chlorine gas originally. What's this going to do? So we need to figure out what x is and which direction it's going. So for every 2 moles of hydrogen chloride that react, you're going to make 1 mole of hydrogen gas and 1 mole of chlorine gas. That makes sense. That's exactly what we said for the previous problem. Now also, this reaction's going to the left because there's no hydrogen gas and no chlorine gas present initially. So right now Q is undefined, and that's not going to make sense. So you're going to have to make the left side non-zero, so the reaction's going to go to the left to make that happen. And reactions will go, you have your initial and your equilibrium, it's going to go straight there. It's not going to go left, right, up, down, middle, back, over. It's like, I'm here, I'm getting to the goal, and it goes. So if it's going to go left, great, it's going to go left. Now we can put this into the icebox. Again, we're trying to find what x is. And so we have the initial concentration set up in here. And now what we did with x is we're minus 2x on the right and plus x on the left, because overall the shift in equilibrium is going to go this way. So if you want, you can think, hey, this reaction's going this way. But we still do write it as an equilibrium because it is actually an equilibrium, so we're going to write it that way. So that's what's different here, is you have the same setup as the previous problem, but now your pluses and minuses are in different spots because you're going to the left and not going to the right. All right, let's scoot this up. And then we do the same thing as we did before, and we'll do this all the time, right? This is the plan, is you then say, hey, what is Kc? And then you from the equation, figure out what the form of the equilibrium constant is. And then you plug your bottom line of this box into the Kc equation. And then you solve for x, right? All this jazz with x in it is equal to 193. Cool, solve for x. I showed you how to do it last time. This one you do it the same way. You just take the square root of both sides and then do algebra to rearrange. And so I'll just give you, here's x. Okay? And then what do we do with this? Well, again, we evaluate this bottom line. Hydrogen, well, that's just equal to x. Easy. So here's your concentration of hydrogen. Chlorine, that's just equal to x. Okay? The hydrogen chloride, well, it's 1 minus 2x. So you have to actually do that and then find what its concentration is. And then again, please double check. So we're going to plug these numbers into the equilibrium constant expression, solve it. Hey, look, we get 193. That's brilliant. Now, it happens to turn out for this problem that we got the same answer as we did for the previous problem when we started with hydrogen gas and chlorine gas. That's not always the case. In these particular two problems, the total number of particles is the same in your equilibrium system, so then you'll get the same concentrations at equilibrium. But very commonly, say this problem you have 0.5 molar and 0.5 molar. In a different problem you have 1.62 molar. Then you're not going to get the same answers for concentration. Because if you look at this form of the equilibrium constant expression, you can increase the number on the top and the number on the bottom. As long as you do so in this ratio, you'll still be at equilibrium. So generally don't expect, if you start from the left or you start from the right, that you'll get the same answers. Sometimes it works out that way, but not always. Okay, let me get generic on you. How do you do this the meta version? First, you write the expression, what is Kc? This also works very well with Kp, so you can do it with pressure. Maybe you have to find what this is, what the equilibrium constant is. Maybe it's like a two-step problem where in the first one you have to find it, then in the second step you use it. Something. Hopefully it's provided. That makes it a little easier. Then you got to figure out which way the reaction's going. If one of the products or one of the reactants is 0, that's easy. Your reaction is going to go that direction to make it non-zero. If not, then you have to figure out what Q is and then compare with K to see which way the reaction's going. Then you're going to set up an icebox and then, evaluate that and figure out what the bottom line is. Whatever plus x, whatever minus 2x. Okay. Then you plug that back into the equilibrium constant expression. I'm in step 5 now. Then step 6, you solve for x. Number of ways to do this. We did the top one. Sometimes you have to solve the quadratic. Sometimes you'd have to solve something cubed and then it gets to be a hot mess. And we're not going to do that to you in Gen Chem. But, that is a possible outcome of this equation, that you have something cubed and you got to do find the root of a third order polynomial, and that gets to be messy. Another thing you can do is you can assume x is small compared to everything else, and then either approximate it, or you can ignore x whenever it's added or subtracted from something. And we do this a lot when we do Ka, because that happens. But generally that's an assumption. You have to make sure it's a good time to use the assumptions, and we'll talk about that later. All right, number 7, once you have x, plug it into your bottom line of your icebox and figure out what your concentrations are, and then please double check. Okay, so then I'm just going to quickly show a little more generic version of the icebox for our generic chemical equation. A and B go to C and D. Again, lowercase is the stoichiometric coefficients. Now, if this reaction goes to the right, which you have to determine whether it goes to the right, if it does, your icebox will look like this, because you have negatives on the left and positives on the right in your change line, because it's going to the right. And then you plug whatever the bottom line is here, you plug this into the expression. All right, so these go here. And then these coefficients, right, they come from the chemical equation. And then you just solve for x. Then once you have x, you plug it into this bottom line, and then you can find what the equilibrium concentrations are. Now, if this goes to the left, well, then the pluses and minuses just change. And, this slide probably looks like it didn't switch around, but it did. So here's going to the left, here it is going to the right, to the left, to the right. You see that all of the negatives and positives switch when you do this. So if you go to the left, it means you're taking away products and you're making reactants. So you have a negative side on the products, or the negative sign on the product side. And then this, fills out the rest of your math with that same sign. All right, this also works identically if you're doing it with pressure. You use the equilibrium constant in terms of pressure. and then you have pressures as all your values in your icebox. And then, but everything else is schematically just the same. It's just you swapped pressure for concentration, and you're using Kp instead of Kc. But otherwise, no problem. Alright, and that's all we have for this video. So again, this is really important stuff that we're going to do and use over and over again in this course. So please take the time to learn it well now, and you're going to thank yourself for it later. Alright, thanks for watching.